DNA replication happens going both sides following the helicase. To make it simpler, we usually use just one side of the bubble to look at it, and that's called a replication fork. You know how like you have a three-way in the road and they say when you hit the fork, take the left side or whatever? So each replication bubble has two replication forks. That's what I've drawn up here. It's my replication fork. So this is origin of replication, O of R. This is where helicase first attached and started unzipping on this side. So it's going to start unzipping and moving down until it either gets to the end of the DNA or hits another open area, so when it knows it can't do it anymore. What I'm going to show you is say, okay, imagine first we've just opened it this much. So first my helicase is here, and helicase is going to go that way. Then as I approach and show it more, helicase has gotten here. Okay. So helicase is going, doesn't care which the direction is. As soon as it hits the replication, the origin of replication, one goes this way, one goes the other way. So they're going to unzip. When it unzips, it exposes the bases. All right. So now you have a template and you can read it. What is the direction for the one that I've created here? And again, it's just, I've created it, I put that 3 to 5 down, 5 to 3. When the enzymes start reading, they have to start also at the origin of replication and based on that orient themselves. So for this strand that I have, the top strands, which way do you think the enzymes that are reading the template are going to go? So if this is from right to left or left to right? Let's make right.
Right to left.
Right to left. Remember, you read DNA 3 to 5. So this is your template. So you have to read for this one going in this direction. That's the language's law. That's how DNA does that. Whereas this strand, you go the other way. Again, so this was the 3'. So for this one, you have to read this way. All right? Let's take the top one, which is the easy one. So you were expecting DNA polymerase to come and say, all right, you see an A, put a T in front of it. You see a T, put an A in front of it. There is no nucleotide here. DNA polymerases are like, I need to have something before me here on the new strand so I can make my covalent bond. I want to attach to the 3' of that pre-existing nucleotide. And the cell is like, sorry, there is nothing there. I want you to initiate this. So to remedy this issue and this problem with DNA polymerases, we have another group of enzymes that are RNA polymerases. Their job is to, whenever they read a template, to make an RNA in response to it. They can read DNA and make RNA. They can read RNA and make RNA. Okay? That's the other beauty of RNA polymerases. They're like, you give us just a sequence, we read it and we make RNA. DNA polymerases are not like, no, first of all, I would just read DNA, I would just make DNA, and I would need a 3' to attach to. RNA polymerases have none of that issue. Their job is like, just give me a base, I look at the base, and I will put my complementary RNA nucleotide in front of it. So that cell has required an RNA polymerase. We named that RNA polymerase primase. kind of like priming the paint, all right? Basically says, sorry, DNA polymerase has this issue. Can you come and just do something for this? You know, get it started. Give it a 3'. So RNA polymerase primase comes and says, sure. So my primase, I'm going to draw primers as red lines. Primase comes and says, an A, U, V, G, G. It will set it up and would read the DNA 3 to 5, make a complementary RNA 5' to 3', and go. That RNA that primase puts down so that DNA polymerase can attach to its free 3' is referred to as the primer. Primer is usually 10 to 15 base pairs long, and it's an RNA. So that's the job of primase. It puts about 10 to 15, and then DNA polymerase comes and says, what are you doing? Get away. This is my job. Now that the 3' is there, the new DNA, I'm going to put it as blue. DNA polymerase 3 attaches here to the free 3' and says, all right, great. I'm going to read it and put my nucleotides, make the hydrogen bonds, make the sugar phosphate, and go. So that's DNA by DNA, I'll shorten it, pull 3. DNA making is very serious for cells, whether it's prokaryote or eukaryote. This is the process that is happening in all of us. DNA polymerases, as they read, they are very careful, and sometimes they might even backtrack and make sure that they've done the right job, so they can even edit. Right? As this DNA polymerase is reading now, helicase is moving, and helicase has gone from here to here. So DNA polymerase here is like, fine, I'll follow the helicase. Every time it gives me a free nucleotide, I'm going to put a nucleotide in front of it. So it will go continue and follows our leader, which is helicase. This strand starts with one primer and then will be continuous. Why? Because the direction of reading and replication follows the helicase. This new strand, they refer to it as the leading strand, because it's continuous and can follow the helicase. That's my leading strand. We'll deal with RNA and all of that in a bit. You can't have RNA independently. All right. Same thing has to happen to this one. However, in here, all the enzymes have to read in the opposite direction of helicase. So, again, DNA polymerase refuses to start. So, let's say all of these jump up at the same time as that's happening here, except for this one, helicase is here, so it goes, all right, let me make a primer for you. So 5', 3', this is the primer. Then again, the 3' is there. Same thing, DNA polymerase jumps on and makes the DNA. By the time this is happening, helicase has moved further down. So they have to play catch up with the helicase. So again, by the time this is done, helicase is here, more bases, again. Primase jumps up, makes a little primer. DNA polymerase goes, and once it gets to this one, falls off. All right? DNA. Same thing, again here, 5 to 3, RNA, primer, goes, hits this one, falls off. RNA, DNA. For this strand, where they have to make it in the opposite direction of helicase, it becomes fragmented, discontinuous. We refer to this as lagging.